decompositions and some recent work on localized measures using wavelets. Okay, so the first thing is from some 200 years ago, the Gauss linking number, which tells you the linking of different curves. So I have some examples here where linking number is 5 on the right, and you have different curves of different linking numbers on the left. And Gauss found a double integral around the curves, which measures this linking integral. The magnetic helicity integral, as introduced by Moreau and Moffat, sort of expands this to a continuous field with field lines everywhere. You just replace the tangent vectors of the Gauss linking inside the Gauss linking integral with magnetic field strengths. Okay, so I'm presenting it as a double integral because that's gauge invariant. But once you use the Biot-Savart integral to do one of them, then you get helicity as integral of A dot B, which is the sort of more famous way of writing it. And that's a slightly corrupting thing because now you can use whatever gauge you like for A. If your volume is bounded by a magnetic surface, then it's gauge invariant. But if it's not bounded by a magnetic surface, then you can be in trouble. So in some ways, the double integral is better. I should say in the double integral, if you see this b of x dot r cross b of y, that's sort of like the helicity density. It's a 2-point correlation function with this funny dot r cross in between. So sort of the purest form of a helicity density is like a 2-point correlation function. And that's something that's useful to think about. In open volumes, one way of doing things is to take the helicity relative to a potential field. So here's the true field, and here's the potential field up above. You don't know what's down below, but it doesn't really matter because you put whatever you like down below and you subtract the two, and then you get a gauge invariant quantity. Okay. There is an alternative which gives you the same answer as the relative helicity formula when you're outside of a sphere or outside of a plane. So the sort of two most popular geometries, or inside a sphere, or in between two planes, let's say. And that is the linking of poloidal and toroidal fields. So if you decompose your field into a toroidal section, which is parallel to, or you have no net flux out, or no flux out of the surface, and a poloidal section where you have no vertical current out of the surface, then you get helicity as the linking of those poloidal and toroidal fields. Okay, and I could say you can write this if you have a succession of nested spheres. You can have a helicity measure on each sphere, or alternatively parallel planes. So you can look at it like this. The poloidal flux in red is linked by the toroidal flux in blue. And again, it gives this idea, gives the same answer as relative helicity outside a sphere or in between two spheres or parallel planes. It can be modified slightly. There are ways of getting things to work if you don't have spheres. In a paper from a few years ago with Gunnar Hornig. Okay, so helicity dissipation rate is, if you're just looking at pure dissipation, and we're ignoring boundary term for dissipation, because in high magnetic Reynolds number plasma that might be small. And what this slide does is show you that the helicity dissipation is bounded by the energy dissipation. So you need a certain amount of energy loss to actually have net helicity loss due to dissipation. You could integrate this in time. You need a length scale. Helicity divided by energy gives you a nice length scale, a dissipation time for that length scale. And you find that the helicity dissipation divided by the total helicity might reasonably be very small for, say, the condition of a solar flare. It might be larger, some small scale helicity near the photosphere. You might actually have to consider it, but for coronal values, it's pretty small. Because helicity dissipation is small, you might vulture thought, oh, well, maybe things will relax to the minimum energy state for a given helicity, which is a linear force-free field. Taylor applied this to reverse field pinches. You need reconnection to get that minimum energy state. And very importantly, you need to know that, or you need to assume that no other ideal invariants survive the reconnection. Havertz and Priest applied this to coronal heating back in 1984. And I'll just put some caveats. You need confinement. Otherwise, things expand to infinite space and you just get a potential field. So you need a Helmut streamer or relaxation within a flux tube. And you do have to kill all subhelicities. So you get a lot of recent work suggests you get regions of opposite sign of helicity developing after relaxation rather than just one uniform thing with showing the net helicity in the entire region. Okay, so I'll go to the main part of my talk, which is sort of decompositions in magnetic helicity. Once you measure magnetic helicity, how do you assign it to different parts of the structures of interest? So I'll go through just a few words in Fourier spectra, self and mutual helicity, twist and writhe, field line helicity. I've mentioned linking of Pareto and toroidal fields. I'll say a bit more about that. And then wavelet methods. So with Fourier spectra, the physical meaning is you're representing a field as a sum of circular polarized modes. And each mode has self-linking, but there's no net linking between modes. When you Fourier transform everything, that div b equals 0 becomes k dot b of k equals 0. You get the Fourier transform of the vector potential A. You define A star of k dot b of k to be your helicity density. And this happens to be gauge invariant, which is very nice. So you don't have to worry about gauge invariance there. So you get a helicity spectrum there. There's some nice properties. There's Parseval's theorem works. So the integral over k of the helicity spectrum equals the total helicity integrated over real space. You get this realizability condition. H of k is less than or equal to k e of k. So helicity at a particular wave number is bounded by the energy of that wave number. And you need a lot of energy to put helicity at high wave numbers. I may have said it wrong, I'm not quite sure, but at small length scales, high wave numbers, you need a lot of energy to put the helicity in. which leads to the idea in turbulence that you get an inverse cascade. Helicity likes to be at large length scales where you don't need much energy. Okay, so there's lots of good things about Fourier spectra in turbulent fields and understanding dynamos and so on. I just want to point out a few caveats, a few things where Fourier spectra sort of don't quite get it. The first thing is where it doesn't always detect helical structure the way you want. So let's say I've created a sort of artificial field here, parallel flux tubes, alternating positive twist and negative twist. And there's a uniform field that's vertical. So that's like the Pareto field, and the toroidal field is varying. So the Pareto field is a sort of k equals 0 state. It doesn't, the vertical field is k equals 0, and but the helicity spectrum will be identically 0 because essentially when you do A of k dot B of k, you're going to reduce to A of z or A of kz in the vertical direction, only having k equals 0 because nothing's happening vertically. And that has to dot with what's happening in the horizontal where you don't have any k equals 0 terms. So what does that mean? Spectrum, the helicity spectrum only detects biases towards positive negative helicity at different length scales. So in the picture, you have this nice length scale, say the radius or diameter of these tubes, but at that length scale, there's equal amount of positive and negative helicity. So you don't get anything in the spectrum. So it's great if you have some bias, maybe Coriolis forces in the northern hemisphere of the sun. Say you have small scale helicity for a particular sign, and then helicity spectrum's good. But if you have a turbulent medium where you have a lot of twist at small length scales, but here it's negative, here it's positive, and it's sort of random, the helicity spectrum won't necessarily get it. So that is a problem to worry about. The second problem is just if you're not doing a turbulence thing, but you're doing a discrete flux tube, let's say, you know that if you Fourier transform a delta function, you just get a infinite sine wave, and you have something like Heisenberg uncertainty. The smaller the object you're transforming, smaller in real space, the wider the spectrum is. So this is from a study from Mahbouba Asghari-Darghi and myself several years ago. We Fourier transformed discrete flux tubes that were twisted and writhed and so on to see what you get. And you do get this sort of wide, wiggly spectrum just because it's a very small, discrete object. So again, that's something you have to take into account when you're doing Fourier analysis. Okay, I'll go on to self and mutual helicity. So if we subdivide your field into different regions, let's say each region contains all its field lines apart from if they're cut off at, say, the photosphere. So you have here a red region and a blue region. Then we can ask for the self-helicity of the red region, the self-helicity of the blue region, and the mutual helicity in between. And the total helicity will be the sum of all of these. Okay, and as we'll see, the self-helicity, if it's a flux tube, can be regarded as twist and writhe, but it doesn't necessarily need to be flux tubes. one region could be a set of sheared loops. Now, I could divide these set of sheared loops into, 5 individual loops, each with each having sort of 5 self-helicities, and 5 times 4 divided by 2, 10 mutual helicities. Or I could take it all as a single region with some helicity and then put it with some other region, and I want to know how those two regions interact. And then you get a self-helicity and a mutual helicity between those two regions. And some of them might be positive or some of them might be negative. So more interesting example here is Sarah Martin's prominence model, where you have barbs and a spine going through and a sort of arcade on top. Then you get various self-helicities and mutual helicities. Here the self-helicities are mostly due to shear as far as the arcade and the barbs are concerned, but some twisting in the spine region. Okay, and then you get self-helicity of barbs of opposite sign to the helicity of the spine and overlying arcade. So in that model, you can test how accurate a model like this is by just going out and measuring these things and trying to see, exactly what the decompositional helicity is. And of course, when things start reconnecting, that tells you how much helicity is available for putting into sending from one region to another. Because the only way to transfer helicity from one region to another is going to be through reconnection. Okay, so so reconnection of 2 flux tubes will convert mutual helicity to self twist plus writhe helicity. Okay, and so there have been some recent papers about this. So you just take helicity, 2 flux tubes that don't have twist, and then you can reconnect them and get some twist. Okay. So I'll go to the next thing, which is twist and writhe. So here's a few examples of twisty things, where you sort of have a central axis that's untwisted, but twist is twist maybe about the central axis. Whereas writhe, one way of defining it is linking number B minus twist number. So I have 2 things where the field lines, the linking number between 2 field lines is -8 on the left or 10 on the right. The twist on the left is -7 something on the left or 10 something on the right. The shape of the flux tube is the same, so the writhe is the same. And the writhe turns out to be -0.72 here. So I'll say a few things about how writhe works. It's the less familiar concept. Looks like something like kinking. So again, helicity in this is just purely from twist, from linking, or from writhe. And you put them all together to helicity will equal twist plus writhe. It's not just the number of turns. If you have a helix, it's also how wide the helix is. So one way to think of it is writhe is the net number of crossings you see from averaged over all possible viewing angles. So if you have on the left a very wide thing from almost all viewing angles, you will see a bunch of crossings, whereas on the right, you'd have to be almost looking straight down to see crossings. So you have much less writhe. There's a fun sort of thing from mathematics that writhe is related to the area of above a Trantrix curve. It actually might be useful in some calculations. I think I have an animation of this. So a Trantrix curve, you take the tangent vector, which is a unit vector, lives on a sphere. So as you go around the curve, the tangent vector draws a curve on a unit sphere. Then you take all the area above that curve and sometimes that area and see how much it's rotated around in a anti-clockwise sense. And that gives you the writhe. It's kind of a neat thing, useful in some things. Okay. Oh no, I didn't want to do that. I want to go to the next thing. And again, writhe is twist, or helices is twist plus writhe. Okay. So it's in the kink instability, internal twist will be converted to writhe. In a stretch twist flow dynamos, you get large scale writhe of one sign, and to compensate small scale negative twist helicity, because you're not creating any net helicity. In the outer convection zone, Coriolis force on the rising tubes might create a large scale positive writhe helicity and a small scale negative twist helicity. So Blackman and Brandenburg will call this bihelical fields. And this is also could be the helices source in active regions. Okay. Oops, there's an example from nice example in plasma fusion of stellarators, and they have to worry about things called ion drift modes. So what I'm going to say might have some interest to people going beyond MHD in solar physics. So the idea, Spitzer's original idea from, I think, 1958 is you don't have a tokamak, which is a nice circular ring. You have some writhe there, either as a figure eight or some more modern versions with just a small amount of writhe. And what does that do for you? Well, I have a sort of funny example, which kind of, so you can feel it in your stomach why it's better might be better not to have a circular tokamak. And that's when things open up again, you go to a Alton Towers or whatever and go on a roller coaster. Now, roller coasters can have spin. They'll spin the riders, and they can have writhe as well, as you see in this yellow version. I don't know about you, but for me, the spin really makes me ill. So I'm happy with the roller coasters where there's zero spin. Writhe is okay, probably. So there's a problem. Supposing you want to design a roller coaster following the track of a trefoil knot. Can it be designed for people like me who don't like being twisted on a roller coaster? Well, if you do that, and this is where it gets close to the stellarator example. Here I have an example with twist. This happens to be the Frenet frame, where the shape of the roller coaster track follows the normal to the curve and so on. But if you could design it with twist equals 0. And actually, I'd rather, even though I get ill, go on the roller coaster that has twist, because as you go around, when you reach the beginning again, you crash. The tracks crash into themselves. They don't join up. Now, so this is called a geometric phase, and it's bad for roller coasters, but it's really good for stellarators, because if you have a wave that goes all the way around, the wave will interfere with itself when it gets all the way around. It doesn't match up and reinforce each other, so that you destroy any resonance that's going on. So writhe is good for destroying resonance of waves that go all the way around. Okay. Now, one thing to know about with helicity is you sometimes see S shapes or loop shapes with in projection S shapes or inverse S shapes. It doesn't necessarily tell you the sign of helicity, because you need the height to measure these things. Okay. And you can, from paper by Tibor Turok et al., you just get writhe as a function of height, can be positive or negative depending on the height of the writhe. Okay. I'll say a little bit about field line helicity, come back to it with the wavelet stuff. So if you remember that helicity at its root is measure of linking. Now linking two on the top right, you see a red and blue things that are linked to each other. And I've drawn it sort of in a braid form so that they wind about each other. So you could also think of helicity in terms of winding, which I've done here. Two flux tubes wind about each other. For arches, maybe you cut them at the top and you just look at each bit, how much it winds about each other. You can still fit it into this form. You just sort of have to cut things at their top parts and see how much each bit winds about each other. So field line helicity measures how much an individual field line links or winds about all of other flux. Okay, so if we're a closed field line, you just say integral of A dot dl. Stokes' theorem, integral A dot dl equals integral B dot NdA, flux enclosed. When you have field lines with endpoints, you have a bit more work to do. A is not gauge invariant. So a good way of doing it is choose Pryor and Yates, the winding gauge, where you get the right answer. It's a particular gauge of vector potential where you get the winding number right. Or some more recent papers where you do a sort of relative field line helicity, and you can get the right answer there in different geometries. Okay, so that will help you because you can map helicity as a function of field line, and that can give you a surface map on the photosphere. Just say at this point of photosphere, you get a particular field line. What is its field line helicity? So that can be very useful. Okay, I think I have some time to review helicity flux before I go on to some more recent work. So helicity flux into the corona is just twisting and also winding of endpoints moving around each other. And a third thing I haven't drawn a picture of is emerging flux. Emerging flux will carry with it twisted flux or linked flux. Okay, and there's some expressions for this in terms of apoloidal and toroidal and B tangent and so on. Okay, so you can get some expressions for that. You can do it with local tracking velocity, and then you don't need to worry about which flux is old flux and which flux is emerging flux. You can do this for energy as well, by the way. If you have small flux elements, and you sometimes have to worry that there are some non-helical motions that can have large fluctuations in helicity flux, which create noise. So if you just have a flux element moving with velocity u, and it's moving around other flux, so there's an A sub p, a vector potential, colloidal vector potential associated with that other flux, then you have to worry about how that vector potential is distributed inside, in the interior of that flux element. Now, the flux element itself has a vector potential, a colloidal vector potential AP, and that AP dot U will be negative on one side and positive on the other side. So its sort of self-helicity has it's just moving in a straight line. It shouldn't add to its self-helicity. So you get equal amounts of positive and negative. So you have to worry, you have to get rid of that self-helicity contribution, at least worry about it. Because if you don't measure it correctly, it'll give you a lot of noise or give you a bad answer. So if you can just look at the self and mutual helicity of each flux element, then you have a better chance of getting things more accurate. Okay, so one thing is just, if you have discrete flux elements, just measure how much their angular velocity is around each other, what their flux is, sum over all the d theta dt's, all the derivatives of winding number around each other. And if you can do it, you can measure the spinning terms, twisting the tube, connecting with point I. Okay. For large-scale helicity flux, if there's an uniform rotation, you're not going to get anything, but you will get helicity flux in the northern hemisphere and opposite sign in the southern hemisphere. So these arrows represent the helicity flux, but there's an equivalent amount going through the equator. So each hemisphere gets a net of 0, but with differential rotation, you're getting more coming through the equator, and that will spin up the flux in the northern hemisphere negatively and positively in the southern hemisphere. So you get a situation like this. Okay, so and that's a very large scale thing, and some of that might be available for use, getting into active regions and so on, and feeding the helicity in the corona, as well as all the small things going on. And still an interesting question relating the input to the solar dynamo to the output, whether you're doing it with Fourier transform wavelet or whatever. How do things come in? How do they go out? What gets lost through the equator, which needs to be addressed as well. How much shorting? It's like a battery that where you have positive charge on one side, negative on another charge. If you let the battery sit around for 10 years, maybe it just loses its charge, and maybe the sun loses a bit through the equator as well. Okay. Okay, so I want to get back to this helicity linking of poloidal and toroidal fields, because if you do want to do fields that aren't in a sphere or a parallel plane or in a plane, then there's a generalization of the idea of poloidal and toroidal fields that will help you. So again, this is a slide from before, helicity integral LT.LP, where T is the toroidal scalar field and P is the poloidal scalar field. The toroidal potential and field due to single oblique flux tube. Well, one thing is that the helicity can be expressed as here LT.LP, that's the toroidal magnetic field dotted with the vector potential of the poloidal field. So it's like an A.B over here, but we could integrate by parts and just get the scalar T times BZ. And what's happening here? You if you have a single flux tube that's at an oblique angle, it's twisting around point 1 in a anti-clockwise sense, and it's twisting about point 2 in a clockwise sense. So you can get positive or negative toroidal potentials due to that. It tells you, so TBZ, it says, if I have a BZ here, I will have a positive toroidal field associated with it. That tells me how much this yellow field line is twisting around a flux tube put here. So that's sort of a physical interpretation of this toroidal potential. Okay. And LT looks something like a dipole field centered over here. It's a sort of difield field associated with the currents parallel to the surface, which are sort of on opposite sides because it on either side of the flux tube. Okay. So if you want to get out of the idea of spheres, okay, well, this might be a bit silly on the left, but it's useful to have half spheres because you want to do the northern hemisphere separately to the southern, because you have negative helicity in the north and positive in the south. The sum is 0. And sometimes you do numerical simulations in boxes. So what do you do then? Here you go into this a little bit. I'll leave the equations in the PowerPoint file if you want to look at them, but I won't say too much because I'll have to go too quickly through them. But the basic idea is you need a normal component of a curl and call that an operator, and try to invert it. And the inverse operator as a gauge problem, it's sort of an integral, but you can set the gauge by saying div v equals 0 and n hat dot v equals 0. So it's sort of unique, and it's unique in a sphere or a simply connected surface. So it gives you a sort of unique toroidal vector potential, poloidal vector, how does that work? poloidal vector potential due to B dot N at the surface. Or you get a toroidal field due to the J dot N at the surface. And that's this inverse operator, D inverse. And this works really great for spheres and parallel planes, a lot of nice magnetic properties. But if you go up to these other surfaces, which lack symmetry, you get into trouble. It's not a very nice, D inverse is not a very nice operator anymore. And the upshot is, I'll just skip these, you can look through them. You get an unwanted field parallel to the surface when you take this vector potential and curl it. Again, it just doesn't work very well. You get spurious extra currents. So you correct that with what I'd call the shape field. And this shape field, then you can add to your regular field, and you sort of get back some of your nice properties of the toroidal poloidal decomposition. And when you do that, it turns out your helicity gets an extra term, which is here on the right. Sort of in essence, it's the poloidal field linking itself. Or you could say it's the poloidal field created by this D inverse linking this special shape field that's arises because non-symmetric boundaries give you a weird decomposition. And that is what you can use to do the poloidal-toroidal decomposition. It gives you an alternative to relative magnetic helicity. The difference between them is relative magnetic helicity. If you measure the relative magnetic helicity of the interior of your surface, add it to the relative helicity of the exterior to the surface, you might not get the total helicity of all space, right? There's an extra term there. Here, with this shape field, you can divide space into concentric spheres, or rather concentric, simply connected surfaces, and everything is nicely additive. Okay. I just want to go to the final topic, which is wavelet analysis. So this is kind of a new thing as applied to helicity, but I think it has some potential for analyzing observations and analyzing simulations. So we saw Fourier transform doesn't give you enough information when you have both positive and negative helicity at the same scale. It's sort of, it's good for biases, but not when you have lots of random helicity, positive and negative at the same scale. So what we want to do is measure wavelets use wavelets to measure the helicity. Okay, and just a brief introduction. Wavelets come out of something of the idea of a window transform. You know, if you take some music and you want to know what notes are being played, you can't transform the whole piece of music because that's several minutes long. You'll just get a mess. You really want to transform every single, just an individual note. So you have a window, you only integrate over time over the length of the note, and then Fourier transform will tell you whether it's middle C or high A or whatever. So here you get this Haar scaling function phi, the father wavelet, is just non-zero over a certain window. But you can go beyond that and have the mother wavelet, which is both positive and negative. And so you sort of window in certain regions, which have both a location and a size, and you can look for fluctuations within that region as well using the mother wavelet psi. So you have a combination of these two, father and mother wavelets, giving you information about what's happening locally. I would need about 3 or 4 lectures just to really get into enough detail so you can use them, but there's a lot of good books out there to look at. Of course, you can't go to the library because the library is closed, but maybe you can find some ebooks. And yeah, so you have each wavelet has a scale, and it has locality as well. So the scales, and usually what's done is the scales go up by factors of 2. Okay, so you have both scale and locality that you can use for your wavelets. It's a lot easier in 1 dimension than 3 dimensions. So you sort of do wavelet transform in 1 dimension, in each dimension, and kind of multiply them. Yeah, I won't go through all of these things. I'll just get to and you just multiply by all the wavelets varying in X and Y and Z, and play around, take sums, and do things. And again, I'll just leave these equations in the PowerPoint in case you're interested. So for something like linked flux rings, if the blue, if they're unlinked, then you get, that's in red on the right, you get things on large length scales. If they're twisted, you get things on more of it is, a higher proportion is at smaller scales. And you can also have little dots representing localization and color the dots darker depending on how much helicity is at that location. So that's the idea of using wavelet analysis. You can also apply it to field line helicity. So C is a sort of winding gauge A. And so if we integrate C dot B, then we'll get, sorry, I didn't say that right. C is sort of this winding number 2-point correlation, and we'll integrate that along the field line to get the field, get the field line helicity. C is winding gauge. I'm sorry, getting confused there. And so we applied this to a model from Dundee, and you can look at the surface and say, what is, at each point on the surface, what is the field line helicity associated with the field line coming through that point? And you get a series of, you get a picture, and that picture changes as the field evolves. Okay, so as the field evolves, you get some reconnections, and you wind up with 2 oppositely twisted flux tubes rather than some messy braided thing. And you can see time is going to the right and scale is going to the left. So this is small scale at the bottom, large scale at the top, very large, at the very top is all scales added together. So things go to twist from the left to the right Here in the second row, it's very large scale, sort of shows the same thing. But when you get to intermediate scales and small scales, things somewhat differ to a great extent. There's a lot of structure at the very small scales that you don't quite see at the large scales. Also, you'll get a lot of, at some scales, you'll see both positive and negative twist going on at smaller scales, but uniform at larger scales. So there's lots of interesting things to analyze there when you use this wavelet decomposition method. Okay, I think I've run out of time, so I will stop there. Thank you for going through those with me.